Today's lesson is on motion. Sometimes it's called particle motion, sometimes it's called rectilinear motion. The type of motion we're going to deal with is all straight line motion. So it's fairly simple types of motion. There are quite a few note cards for today. Hopefully you've already got all of those and have gone through them and looked at those in detail, because we're going to assume that you have. So here's our first example. The position function is t cubed minus 6t squared, and it's moving along an s-axis. An s-axis is an arbitrary axis, not necessarily the x or the y. It's just saying that it's along this straight line, y equals s. Part A says to use your graphing calculator to show the graphs of position, velocity, and acceleration versus time. So we have our position function, but we need our velocity function. So we're going to get the velocity function by taking the first derivative of the position function. And that's going to give us 3t squared minus 12t. We need the acceleration function, which is the first derivative of the velocity, which is the same thing as the second derivative of the position function. And so I'm taking the derivative of this one that I just got for velocity. That'll give me 6t minus 12. So now we're going to put those in the calculator. This is what it's going to look like. Now this window has been adjusted, and you might have to play with it a little while before you find a good viewing window where you can see all three graphs. Here's my window. The cursor is on top of the negative, so x-min is -5 here, but of course yours doesn't have to be exactly the same as mine. So on this graph you can see the cubic function is the position function right here. The quadratic is the velocity, and the linear is the acceleration. So part B says analyze the motion of the particle for times greater than or equal to 0. So really I'm not concerned with anything back here in the negative time. This is my time axis, and then the y-axis represents position, velocity, and acceleration depending on which curve I'm on. Now the time here is counting by ones. Okay, so let's talk about the position to start with. My position begins at 0, which means I'm starting kind of at the origin, and it moves downward or to the left everywhere where the graph is decreasing down here. Then the position increases, hits 0, which means it's returned to the origin, and now it's moving off in the positive direction. Now, the velocity graph tells me direction of travel. When the velocity is negative down here, that means I'm moving to the left or down, depending on whether I'm on an x-axis or a y-axis. Moving in the negative direction from 0 seconds to whatever this other x-intercept is here. If you set that equation equal to 0, you could find out, looks like about 4. So negative velocity until 4, then that's when I have a direction change. Notice that correlates to the minimum on my position curve. So my direction is going to change then and start moving back into the positive direction, and it's positive for the duration of motion that's going on. Now my acceleration begins negative and then hits a 0 and then becomes positive. Okay, so let's see, what do we need to do next? When is the particle stopped? Okay, so the particle is stopped when the velocity equals 0. So where does the velocity equal 0? Well, let's take our velocity function, 3t squared minus 12t, set it equal to 0. This is factorable. 3t times t minus 4 equals 0. So 3t equals 0, or t minus 4 equals 0. So I have t equals 0, or t equals 4. And if we were to get any negative times in here, we would throw them out because we're only working from 0 on. So the particle is stopped initially at the time t equals 0, and again at the time t equals 4. That's where the particle is stopped. And then D, determine the signs of the velocity and the acceleration. Where is the particle speeding up? Okay, I'm going to erase and make a little sign chart here. So here's the velocity function, the acceleration function, and the time. Now, I am going to look at the zeros of these functions. By the way, what were the zeros of the acceleration function? 6t minus 12 equals 0, so that means 6t equals 12. Divide by 6 on both sides, t equals 2. So I have a 0 on the velocity function at 0. I have a 0 on the acceleration function at 2, and I have a 0 on the velocity function at 4. I might want to pick a numbers between and beyond these, but I really don't need to go to the left of 0 because it's not even included in my domain, so that's kind of irrelevant to the situation. So I kind of want to just pick numbers on each side of these, which would be easy. Between 0 and 2, 1. Between 2 and 4, 3. And beyond 4, we could go with 5. Now let's talk about the signs of these. My velocity curve is the quadratic one. So when it is at 0, of course, the time is 0, the velocity is 0. Then it is negative until I get to the time of 4, where it's 0 again, and then it switches to positive. Now the acceleration is this straight line here, and it starts out negative, it hits a 0 at 2, and then it's positive beyond that. Okay? So the question asked us, when is the particle speeding up? The particle is speeding up whenever the sign of the velocity and the sign of the acceleration are the same. So you see, pardon me, right here the signs are the same, and right here the signs are the same. Nowhere else in our sign chart are the signs the same. So we would say that it is speeding up on the interval from 0 to 2. Remember, 1 was an arbitrary number we picked to see what was going on between 0 and 2. And also on the interval of 4 to positive infinity. Okay, that's where the signs are matching of the acceleration and the velocity. That's when it is speeding up. If it had asked us when it's slowing down, which it could have just as easily done, or sometimes they ask for both, it is slowing down when the signs are opposite. So that would be from, let's see, 0 is the beginning of our domain. From 0 to 2 we are speeding up. We have matching signs. But then from 2 to 4, in this interval, the signs are opposite. So from 2 to 4 it's slowing down. And then beyond 4 they're the same again, so it's speeding up. Okay. Our next question. Oops, skipped too far. Example 2. We're starting with a new function now. The position of a particle is given by x of t equals 1/3 t cubed minus t squared minus 3t plus 4. Find the total distance traveled on the interval for times between 0 and 6, inclusive. Okay, so we're given an x of t equation. That means we are moving right-left direction. That means when our velocity is negative, we're moving to the left. When our velocity is positive, we're moving to the right. Now, we want to find the total distance traveled. From your note cards, your total distance traveled is going to be adding up the absolute values of the differences in the position between all resting points. So the first step to finding the total distance traveled is to find the resting points. What are resting points? Places where you're not moving. Places where the velocity equals 0. So the first thing I want to do is find the velocity equation and set it equal to 0. So v of t for this would be t squared minus 2t minus 3. And I'm going to set that equal to 0 to find the resting points. Is this factorable? Yes, it is. Set each factor equal to 0, t equals 3, or t equals -1. Now, this -1 we can cross out because it does not fall within our time interval from 0 to 6. So really the only one we need here is one resting point at time t equals 3. So, we're going to find the absolute values of the differences in position between all resting points. Well, we're going to have a starting position, so we're going to need to figure out what x of 0 is. We're going to need to have a resting position at time 3, so we're going to need to figure out what x of 3 is. And we're going to need a final position, which is going to be x of 6. So, I'm going to substitute a 0 in for all of these times in my position equation, which is going to just give me 4. Now, I'm going to substitute a 3 in for all 3 of those t values. And I'll let you play with that arithmetic. That's going to give you -5. And I'm going to substitute a 6 in for each one of these t values in my position equation to see where my final position is. And after you do the arithmetic, you will get 22. So this position starts at 4, goes to -5, and then goes to 22. Now I want the total distance traveled. There's a couple of different ways you can do the math, but we're looking at the absolute value of the differences in the positions. So it's going to be like your final position for an interval. I'm going to start with the interval from 0 to 3. So I'm going to say -5 subtract 4 in absolute value bars. And add that to, now I'm going to do this interval from time 3 to time 6. Final position is 22 minus starting position -5. And now I just do this arithmetic. -5 minus 4 is -9. 22 minus -5 is 27. The absolute value of -9 is +9. And the absolute value of 27 is 27. 9 plus 27 gives you 36. Your total distance traveled is 36 units. Now another way that you could have thought of this is, oops, part of my 5 went away. How far apart are 4 and -5 on a number line? They're 9 units apart. -5 is 5 units to the left of the origin, 4 is 4 units to the right. That's a total of 9 units apart. How far apart are -5 and 22 on a number line? 27. Add those two, you get 36. So there's different ways you can kind of think about that there. So long as you arrive at the answer of 36, you're in good shape. Alright, our final example. A ball is thrown upward from the top of a 480-foot tall building with an initial velocity of 64 feet per second. Use calculus to find the following, and then we have A, B, C, D, E, many things to find. We are going to use a calculator on this example because a lot of the answers come out to be irrational. Generally speaking, on the AP Calculus exam, if the answers are kind of yucky, mostly irrational, you could have fraction answers, but not usually square root answers. They will usually put that on the calculator portion. So we're going to do this one with a calculator. Now, first thing it says to do is find the maximum height achieved by the ball. Well, before we can do that, we kind of need to write a position equation given the information in the problem. And to do this, we are going to use the free fall model, which was your last note card for today, and that is S of t equals S sub I, which means your initial position, plus V sub I, which is your initial velocity, times time, minus 1/2 gt squared. And g is a constant, the acceleration due to gravity. Since this problem is working in feet per second, we're going to use 32 feet per second squared as our velocity due to gravity. And so when I plug 32 in here, that's going to be 32 times 1/2, which is 16. So negative 16t squared. Now, the way that I kind of set this up in calculus is with a positive acceleration due to gravity, but there's a minus in the formula. Some textbooks will put a positive in the formula, but then say that gravity itself is a negative force. A negative acceleration, I should say. So it works out either way, whether the negative is in the formula or whether the negative is with the gravity. It just depends what book you're looking at, which way they'll do that. So, what else do I need here? An initial position. It tells me that it starts at 480 feet. So there's my initial position. And my starting velocity is 64. So 64t. There's my position equation. 16 is actually a factor of all of these two, FYI, but that's okay. Alright, find the maximum height achieved by the ball. Okay, the ball is thrown up, it reaches its maximum height, then the ball falls back down, free fall. So we want to know, what is this maximum height that it reaches? That is going to be when the velocity is equal to 0. Remember, a maximum is when the first derivative is equal to 0. So I'm going to take my velocity of this equation, v of t, and first find the equation, which would be 64 minus 32t. And I'm going to set that equal to 0. Add 32t to both sides. Divide by 32 on both sides. T equals 2 seconds. Okay, so that wasn't what they asked me to find. That tells me when the maximum height is achieved, but it doesn't tell me what the maximum height is. So to get the actual maximum height, now I need to plug 2 in to this position equation to find out how high it went. So plug 2 in for t here and here. You can do that using your calculator. S of 2 equals 544 feet. And that's the answer for part A. Okay. So we got part A done. Now let's look at part B. Find the velocity of the ball at the instant when it hits the ground. Okay, well, I don't really know when it hits the ground yet, so this is another two-step problem. First, I need to figure out when it hits the ground. So it's going to hit the ground when its position, S of t, is equal to 0. So I'm going to put 0 equal to 480 plus 64t minus 16t squared. And how do I find the zeros of that? Well, if it was factorable, I could factor it, but it's not, which means I need to use the quadratic formula, or my calculator. You could potentially have to use the quadratic formula on a test in my class by hand, but this one the numbers get really big too, so I wouldn't probably choose one like this. Make sure that you are familiar with your quadratic formula though. If you go into your calculator and you look for the zeros of this function, hopefully you remember how to do that. Plug this into y equals, type it in, 480 plus 64t minus 16t squared. Go to your graph, hit second, calculate, number 2 for zeros. It asks you left bound, so you cursor until you're just to the left of the 0. We only care about the positive 0. Then arrow to the right for right bound, hit enter again for guess, and you get x, or your position, is approximately equal to 7.83095119. You need to use all those decimal places when you're plugging in for the next step, because premature rounding is not allowed on the AP exam. So when it wants me to find the velocity at that instant when it hits the ground, oh, I'm sorry, this is not the position. The position, I made a mistake. The position is not equal to 7. The time when the position is 0 is equal to 7.83095119. So I'm going to take my velocity function and plug in that decimal with all of the decimal places the calculator gave me. $7.83095119 to find out what the velocity is. And then this is my final answer for the problem. So this answer I will round to 3 decimal places. So it's negative 186.590 seconds. Oh, feet per second. Sorry, that's the velocity. Feet per second. All right. Part C. Find the velocity. Oh, let me get a new page that's not all written over. So we got A and B done. Find the velocity of the ball at the instant when the ball is 192 feet above the ground. This problem is essentially the same as the one we just did, except for we're going to say 192 is the position. And so I'm going to set 192 equal to my position function to get the time when the ball reaches the height of 192. So I'm going to subtract 192 from both sides, which will give me 0 equals 288 plus 64t minus 16t squared. Put this into the calculator, get the zeros there. The 0 for this one is time is approximately equal to 6.69041576. And then I'm going to plug that into the velocity function for the time. Just like I did on the last problem. And that will give me a velocity of negative 150.093 feet per second, rounded to 3 decimal places. That one I can round because it is the final answer. Okay. We've got A, B, and C done. Part D. Find the average velocity of the ball during the time the ball was in the air. Average velocity is a note card, and it's basically your slope formula. Position at the final time minus position at the initial time divided by final time minus initial time. So I need to figure out, where do I start and where do I end? Let's see here. Our final time is going to be when it hits the ground, which is what we figured out in part B. So from part B, we remember that it hits the ground at 7.830951 895. I don't remember how far we went with that. So our initial time is 0. So the final position we also got in that part B. No, we did not. Final position. Oh, well, the final position is 0. That's when it hits the ground. Okay, so the final position is 0. The initial position, it started at a height of 480, divided by the 7.831 minus 0. I wouldn't round that off in your calculator. Negative 61.295 feet per second gives the average velocity. Alright, last one. E, find the average speed. That's going to be total distance traveled over elapsed time. The time is still the same as it was before, the 7.83. I would not round that off. The total distance traveled, the ball goes up for 544 feet when it reaches its maximum, and then it goes down to the ground, which was 480 feet. So it goes 64 up from the height of the building, then down that 64 plus the 480, which is 544. That's your total distance traveled. And when you divide that, you get 77.641 feet per second.